Hey everyone, welcome back. Ready to get our science hats on and dive into something fascinating.
Absolutely. Always up for a good deep dive.
Today, we're tackling a topic that might seem simple at first glance, but trust me, there's a whole lot more going on beneath the surface. We're talking about diffusion. And to guide us on this journey, you sent in some Feynman, right?
Yes, our listener wants to go beyond the basic definition of diffusion.
And Feynman's the perfect guide for that, isn't he? Even
Yeah.
with something like diffusion, he finds a way to make it mind-blowing.
Right, because he starts with something so fundamental, how often molecules collide with each other in a gas.
Like a molecular mosh pit. I love that visual. But he doesn't just talk about how often those collisions happen, does he? He takes it a step further with this idea of the mean free path.
And that's where it gets really interesting, because mean free path isn't about the time between collisions. It's about the distance a molecule travels before it's likely to bump into another one.
Okay, so help me wrap my head around this. Why is the distance so important? Wouldn't more collisions, meaning a shorter distance between them, actually make things happen faster? Like, wouldn't that make heat transfer faster?
You'd think so, right. But here's the thing, and Feynman explains this beautifully, how fast heat spreads through a gas. In a typical container, at least, it doesn't actually depend on how densely packed those molecules are.
Wait, really?
Yeah, it's counterintuitive, but it all boils down to that mean free path.
Oh, are you saying that how crowded those molecules are doesn't matter as much as we might think?
Exactly. Because think about it this way, a denser gas, yeah, that means more molecules,
Hmm.
right? So there are more chances for those molecules to bump into each other. But, and this is key, each molecule also has a shorter distance to travel before a collision.
So it's like a trade-off. More molecules, but less space to bounce around.
Precisely. It's like a crowded dance floor versus one with a bit more room to groove. You might bump into more people in the crowd, but you're also more likely to run into someone quickly, even with more space, because you can move faster.
Okay, that makes sense. So it's not just about how often they collide, it's about how far they travel between those collisions.
Exactly. And that's why the density of the gas doesn't directly impact how fast heat flows through it.
That is seriously mind-blowing. So density is kind of a red herring then. It all comes back to that mean free path, how far those little particles can zoom around before causing a ruckus.
You got it.
This is why I love diving into these topics. You start with something seemingly basic, but then bam, Feynman hits you with these incredible insights. It completely changes how you think about something as fundamental as heat.
So we've got all these molecules bouncing around, right? Seemingly random chaos, but then Feynman throws in another layer.
Okay, I'm intrigued. Lay it on me.
He introduces these two forces that can act on these tiny particles.
Two forces. All right, let's break it down. What are we talking about here?
So the first one he calls external forces. And a really cool way to picture this is to imagine dropping a big, heavy molecule, like a bowling ball, into a container full of lighter gas molecules.
Okay, I'm visualizing it like a bowling ball in a bouncy house.
Right, exactly. But here's the thing. Gravity is pulling that bowling ball, that heavy molecule, downwards, but its journey is anything but a straight shot.
Right, because it keeps smashing into all those lighter molecules.
Exactly. Constantly getting jostled around, bumping into things. And that kind of chaotic path, it leads to this concept of drift velocity.
Drift velocity. So i- is that just how fast the heavy molecule makes it down to the bottom, even with all those detours?
You got it. It's like, on average, how fast is it progressing downward, even if it's taking this crazy zigzaggy route to get there?
Okay, I'm with you so far. So that's external forces, the bowling ball and the bouncy house. What's the second force?
The second one is what Feynman calls internal forces. So imagine we introduce a bit of a different gas into our container, a special gas, let's call it. But this time, there's no external force like gravity acting on it.
Okay, so no downward pull this time. Gotcha. What happens to our special gas? Does it just hang out?
Not quite. Even without an external force telling it where to go, our special gas is still going to spread out over time. And that, my friend, is diffusion in action.
So even without that external push or pull, just the random collisions with the other gas molecules, it's enough to make it spread out.
Exactly. Those random collisions create this natural spreading, almost like a molecular game of telephone, where the message gets passed around just by bumping into each other.
I love that analogy, but now I have to ask these two things. The drift we talked about with external forces and then diffusion with those internal forces, are they totally separate? Or could they be connected somehow?
That is a fantastic question. And you're right to be sensing a connection there, because get this, drift and diffusion, they seem like totally different things, but they're actually deeply intertwined.
Wait, really?
Yeah, Einstein was actually the first to really recognize this connection, and Feynman demonstrates it beautifully by showing this direct mathematical link. It turns out that the easier it is for a molecule to drift under an external force, so think back to our bowling ball, how much it gets jostled around, the faster it'll also spread out on its own through diffusion.
Whoa. So a molecule that's easily swayed by an external force is also more likely to wander off on its own. It's like these tiny particles have a mind of their own.
Right. They're influenced by their surroundings, but they're also kind of rebellious, always up for a bit of exploration. It's amazing how complex these seemingly simple particles can be.
Okay, so we've been on this incredible journey into the world of molecules, collisions, drift velocity, and this whole diffusion dance. But let's zoom out for a second. Why does all of this matter? What's the big takeaway for our everyday lives?
That's the beauty of Feynman, isn't it? He doesn't just leave us in the theoretical weeds. He brings it all back around to show us how these tiny invisible processes explain the stuff we experience every single day.
Exactly. So how does he make that connection? What's an example of that?
Well, take heat, for example. You know, that feeling of warmth you get when you're sitting by a fireplace on a cold night.
Oh yeah, definitely.
Well, that's all thanks to those tiny molecules we've been talking about, zipping around and transferring heat energy through those collisions.
Wow, so that cozy feeling by the fire, it all boils down to those microscopic movements. It's mind-blowing when you think about it.
It really is. And it's not just heat. Feynman also talks about how these ideas help us understand electrical conductivity.
Oh, right, the movement of those charged particles, the ions.
Exactly. It's all influenced by these same principles of diffusion and collisions.
It's amazing how something so fundamental can explain such different phenomena, from feeling warm to turning on a light.
It's all connected. But, and here's another point Feynman makes that I love, he also reminds us that even our best models, even the most elegant equations, they have their limits.
Oh, I see what you mean.
Yeah.
So it's not like we have it all figured out.
Exactly. There are always going to be those edge cases, those extreme situations where our normal understanding might not quite cut it. Like Feynman talks about what happens when a gas is so incredibly spread out, so diffuse, that collisions between those molecules become super rare.
So what happens then? Does everything just grind to a halt?
Not necessarily. But our typical equations, the ones that work so well in more normal situations, they might not give us the full picture anymore. It's a good reminder that science is a process of constant exploration, always refining and expanding our understanding of the universe.
It's like we've illuminated this incredible path through the forest, but there are still those uncharted territories out there waiting to be discovered, and that makes it all the more exciting.
Absolutely. And speaking of exciting, here's something else to ponder as we wrap things up. Feynman focuses on gases in these lectures, but these principles, this intricate dance of diffusion, it's not confined to some lab experiment.
You're right, it's happening all around us all the time.
Exactly. From the scent of fresh cookies spreading through a kitchen to the way nutrients move through our bodies, it's like a hidden force shaping the reality we experience every single day.
It makes you wonder, what other examples of diffusion are we missing? What else can we uncover by looking at the world through this lens of tiny particles in constant motion?
I don't know about you, but I'm ready to go on that adventure.
Me too. And on that note, we'll leave you, our amazing listeners, to do some exploring of your own. Keep those molecular mosh pits in mind, and who knows what you might discover. Until next time.